Yeah. I would recommend that because I think that's still it's still
All right.
something that
Hello everyone.
want to be.
So this is the
For me, it's
promised
just knowing
lecture video on
coming back
part
to the
7C,
questions with them.
frequency response of
This is
CE amplifiers. All right. So let's get started.
we'll call this
So first thing,
the inference is
today
driven by
we're
the
going to be
background. We
talking
don't
about
have a lot of friends
an output pole, no,
but we've had
a
a lot
specific
before.
technique, no, that requires that
So
actually
so that it's
um
not
ends
and
up
that
a
the
circuit
pure
technique that ends up
this is just
giving
not
us
the
an
kind
output pole,
once it
a circuit
there's
technique
like
that ends
just
up
one
giving
more
us an input pole, no,
one more
and something called a Miller capacitance, which in fact actually gives us
so
both an input and an output pole, and also zero, no.
just that
So
it
basically, we can also with these three, now we can combine these three in order to generalize what we can expect now when we have bypass and coupling capacitors. All right. So first off, let's talk about the um what happens when we introduce a bypass capacitor. So a bypass capacitor or rather an AC bypass capacitor allows us to basically shunt shunt a specific port of the circuit to ground to prevent any high voltage very fast spikes from propagating into the circuit and allow us to send it to ground immediately without it going through the circuit itself. No, that's what a bypass capacitor is supposed to be
right now promotions
useful for. No, but introducing this bypass capacitor logically affects the frequency response of the system. No, we can actually assume for now that the BJT does not have parasitics, but the presence of the bypass capacitor will still affect the circuit in enough, no, such that even without the parasitic capacitances, just the bypass capacitor will, well, we call it load capacitance here, will introduce a pole in our voltage gain response, no. So in order to solve for the two-port voltage gain, no, voltage gain, we need V out over V in at no load. We use I out equals 0 because if we use V out equals 0, then we wouldn't be able to calculate anything, no? So to do this, we just do KCL at V out. Basically, that's V out over Z out, no? So this is Z out, basically, plus the current over in this dependent source, which is GM VBE. Rearranging the equation, we simply get that AV is equal to negative GM Z out. No, it's basically just GM Z out, right? So this makes sense. But this is not yet in the form that we are familiar with when we expect to receive information for frequency response, right? So we need to rearrange it, right? So it's kanina, no, it was negative GM RC parallel 1 over SCL, right? So rearranging this, you can get a form like this, no? A negative GMRC over the pole factor, right?
So you would still recommend.
So this is basically structured like follows, no? We have a gain at low frequency, let's call that A0, and then we have a multiplied pole, J omega over omega P, or S over omega P, whichever one is preferred, no, when you write it. So basically, A0 here becomes negative GMRC, which is what we expect, right? It's a common emitter amplifier. We know the gain of a common emitter amplifier. It's GM times the load resistance. But now, it also it falls off at high frequencies. No, you can see this in the next slide. So the magnitude response of our voltage gain now has a omega naught. No, omega naught here is the pole, no, is the pole frequency that we were expecting, which is RCCL, no? And the phase response is also a single pole phase response. The only notable thing here, though, is that it starts at 180 degrees instead of 0 degrees. Bakit? Well, that's because of this thing, no? Negative sign. So the negative sign adds a flat 180 degrees to the phase, no? Which kind of makes sense, right? If a positive number, so let's say we have this complex plane right here, no? So this is the reals and this is the imaginaries, no? Let's just say that's I. So if a positive real number, given a positive real number, it would be pointing to the right, no? But if you negate that, it would be pointing to the left. So basically, what happens when you add a negative sign is that magkakaroon ng 180-degree rotation dun sa complex vector, right? Which means that we add a flat 180 degrees to phase when the gain, when the number is negative to begin with, right? Kung may negative sign tayo, which means it's a times -1. So yun yung nangyayari. But other than that, no, we still add the phase of one pole, no? So we still add the phase response that is expected of a single pole system. So we subtract -90 degrees over time as we get from 1 decade before the frequency of interest, which is RCCL, 1 over RCCL, and a decade after the frequency of interest, which is also RCCL. No, so we just added the expected frequency response that we knew already, right? So this one would be 0 degrees, and this one would be -90 degrees if this were positive, right? But it's not. It's a negative gain, no? It's a negative A0. So we had 180, and then it was 180 plus 0 at the top, which is 180, and 180 minus 90 at the bottom, which is just 90. All right? So that's how, so basically we know the magnitude and phase response from the Bode plots. No, we don't really have to do all of these. But again, no, you can get the magnitude and phase. Magnitude equation is AV star, and the phase is just arctan of imaginary over real. No, if you forget how to do this, this is just you can derive this from SOHCAHTOA, and you can derive this from Pythagorean theorem, no, from the complex plane example that I have shown here. Right. So next, the reason that so okay, what do we know so far? We added a load capacitance to the circuit and ended up with an output pole, right, for the voltage gain. No, but we can also think of this as adding a frequency response to each to the impedances of the system. No, so basically, since AV is equal to negative GM R out, no, in this case it's now an impedance Z out, right, because it's RC parallel CL. Then basically we can actually attribute the pole, no, the appearance of the pole to the CL changing the output impedance. So if we solve for the two-port output impedance, again, V out over I out, given that V in is zero input. So we can calculate Z out like this, and we find that it's just, well, obviously, no, it's RC parallel 1 over J omega CL. We know this from previous classes, no? We can rearrange that to just RC with a single pole, no? So at low frequencies, we have RC, and as it gets higher, we expect it to go down because it has a positive pole right here. Well, okay, doesn't matter if it's positive or negative over here. No, it could be negative again from the lessons. But that only changes the phase response, not really the magnitude response of this system. All right. So basically, what we did, no, when we added the load capacitance, really, is we basically made the output impedance complex, right? We made it RC parallel a capacitor, no? And what that did is it forced RC to go down at high frequencies, which is what you expect, no? Like an RC system versus an R would just be straight like that, no? But when you add the capacitance, it starts being a low pass filter, no? And the low pass filter acts like this. You get a 20 dB per decade, by the way, right? 20 dB per decade. So a negative 20 dB per decade roll off at 1 over RC CL. And that's for Z out, no? So since we have that as the output impedance, and confirm with me, GM, no, the transconductance stays the same for this entire circuit. It stays the same, no? So GM is still GM. Okay. Quite frankly, this should be this makes sense, no? Bakit? Kasi kapag sinort natin yon, matatanggal si RCCL. The short circuit output current is basically just GM-VBE. This is still V in, so it should still be GM. Diba? All right. So yeah, GM is just a real number, no? So what's the frequency response of a real number is just a constant in the magnitude response, and it has zero phase, no? Zero phase or 180 phase, depending on whether or not it's positive or negative. GM is positive in this circuit, no? You know that because it's a CE amplifier. So also, the input impedance is just, well, R pi. It's really just R pi, no? Because we short this, these two disappear, becomes a regular CE 2 port, no? So these two disappear, becomes a regular CE 2 port. We see that it's R pi, no? Because V in over I in is logically R pi, no? But see, when we got the output impedance and the transconductance, now we solved for the output impedance and the transconductance separately, but if we multiply them, no? So GM, Z out, no? And we still get negative GM times RC over 1 plus S over S RCCL, which is the same as we got for gain. So we can interpret we can interpret adding the output load capacitance as adding a frequency response to the output resistor and nothing else to the circuit, no? So that's what an output load capacitance or shunt, like, okay, output load capacitance, shunt capacitance, bypass capacitor, can't call it with many names, but all it does really is give a frequency response to the output impedance, which in turn changes the gain such that it gives a magnitude and a phase response to the gain as well, no? With the pole being 1 over RC CL. All right. So next, no? Well, okay, this summarizes that one. So next we can have an input pole as well, no? So we now have a bypass capacitor at the front, and we now have also a bypass capacitor at the back. We call that C pi, no? Because it's part of the input side, no? And you call the input capacitance of the BJT an R pi, right? So it logically could be named C pi. All right. So we introduce C pi. And what does this basically do? Well, what this does is it becomes a parallel, no? It merges with R pi as an impedance, so we can interpret R pi as turning into a Z pi, which is R pi parallel 1 over SC pi. All right. So now that we have that Z pi, no, we can get the previous amplifier. No, it's an amplifier. Well, it's an attenuator. No, but we have a voltage divider between RS and Z pi over here. No, so the voltage divider gives us this equation below: Z pi over Z pi plus RS. That's the ratio between VBE and Vin. No, because VBE is Vin times the voltage divider. So, giving back what Z pi is supposed to be, no, with this equation, then we can solve for the gain, no, of that side of the circuit. We find that this is R pi over R pi plus RS plus SR pi RS C pi, no. So this is actually a little pretty. You'll see it later on, no? But for now, we're going to be actually, okay, nandito pala sa baba. So you can factor out, no, R pi plus RS from the bottom. So we have R pi over R pi plus RS times 1 plus S times something something, right? And that something something is already here, no? S C pi R pi RS over R pi plus RS. And this form is something that's familiar to us. That's R pi parallel RS, right? And this becomes something that's a little ugly, but trust me, no, this makes sense. No, it becomes of the form a gain, right? A low frequency gain and a pole, which means which just dictates how it changes over the frequency domain. No, so now we have the flat gain, which is R pi over R pi plus RS. Now the low frequency gain, which does make sense. No, it's R pi over R pi plus RS. That's how VBE is affected, or that's how the expected input of the amplifier is going to go down because of the presence of a supply resistance and then input resistance in the BJT. No? So we usually still expect this to be still very close to 1. Bakit? Kasi mababa si RS most of the time, mataas si R pi most of the time, right? Okay, we want R pi to be high, is what I mean. And also, no, we find that the input cap introduces a pole, no, which will propagate through the system, no? So once we solve for V out, we will find na lalabas din tong pole na to. That is 1 over C pi R pi parallel RS, no? So this is another pole that appears. And to me, an intuitive way of interpreting the appearance of this pole is that this is the input of your amplifier, basically, right? This is the input of your BJT amplifier, and looking into all sides, it finds C pi, RS, and R pi, and and R pi is parallel to RS if you look from that side of the circuit, no? But anyway, that introduces a pole to the pre-input of the amplifier, no? So now that we have that, we can just apply the expected gain of the next stage, no? So we now have VBE, and well, VBE is the input to this amplifying area right here, no? So GMVBE times Z out, no? GMVBE times Z out is equal to negative V out, right? Right? So now we have that. So V out over VBE is, well, okay, we basically actually know this as well, no? From GM RC parallel 1 over SCL, no? Because V out over VBE, we just put this down. Now it's GMZ out. This is basically that, no? And then we just expand the parallel in order to make this into a form that's familiar to us, no? And now this form becomes an A0, or okay, well, we've overused the 0 number. It's an A2 now. It's an A2 with a pole. No? So it's an A2 with a pole. A2 is GMRC, and the pole is 1 over RCCL, which is something we already know. Bakit? Kasi the latter half does not involve an extra capacitance. So it basically becomes the circuit that with an output pole that we had earlier. No? So its gain is GMRC and its pole is RCCL. No? We basically could have used what we solved for before. No? Note that this is still this is an inverting amplifier. No? So combining both, no? Both gains, we find the overall gain, which is A1, A2 times both the poles, no? And also, remember that the other side is inverting, no? So may -1 doon. So the A2 is inverting, no? A2, we removed the -1 from A2, put it here. So just remember to add on 180 degrees to the phase response, no? So the low frequency gain would be GMRC times R pi over R pi plus RS. Now, this is when you know you're probably correct because GMRC is the usual expected gain, and this is the voltage division result, no? This is the result of having to voltage divide between R pi and RS at the input of your amplifier. We've already seen this before. The only thing that's, well, the things that are new is the contribution of the output capacitance, no, which is a pole 1 over RCCL, and the contribution of the input capacitance, no, which is a pole that's R pi parallel RS times C pi, no? So this is what this is the basically the analytical solution for the input the C amplifier with the bypass cap at the input and the output, no? So it would look like this, right? The magnitude response would be would have two poles. So at first, no, you encounter the first pole, you go down by 20 dB per decade, and then you encounter the second pole, with which you go down by another 20 dB per decade, compounding together to form a -40 dB per decade slope, no, at very high frequencies. No, so we don't know how close these two are together, but for the magnitude response, it doesn't matter. For the phase response, it does matter. No? So there are multiple cases, but it depends kasi kung nasan sila relative to each other, right? Because the phase response, the influence of the poles in the phase response is within the 2 decades that are around them, no? So basically, if they are 2 decades apart, no? If they are 2 decades apart, here they are, no? So what omega P2 is 100 times omega omega P1 is 100 times omega P2 here. Then your Bode plot, no, of the phase response is going to be a flat 90 down here. Tapos dapat magsa-strain that out, right? But because of the influence of omega P1, bababa ka pa by another 100 by another 90 degrees, no, for a total of minus 180 dito sa baba. Remember, our original gain was negative, so we had 180 minus 180. This turns out to be 0, no? Right. But it could also be that they're very far apart, in which case, no, the contribution of omega P2 ends completely before the contribution of omega P1, but still, it's a total of 180 degrees minus 180 degrees at the end, no, which is 0. It could also be that both poles have an influence that overlap. No, this means that omega p1 is less than 2 decades away from omega p2. No, in which case we have a 45-degree decline. No, starting from omega 0.1 omega p2. No, so this is omega p2's area of influence, but this is omega p1's area of influence, no? So in which case, for this area, you would have a negative 45-degree slope. For this area, you would have two negative 45-degree slopes in your boundary plot. So magiging 90 degrees per decade yung slope dyan. Tapos, at this point, wala na yung influence ni pole number 2, in which case, babalik ka sa 45 degrees. And then here, no, wala nang influence yung poles. No? So flat ka na ulit doon. Kaso, in the end, what we have is magzi-0 degrees din sila sa dulo because it's 180 minus 180. The total influence of two poles at very high frequencies. All right? So, deriving the other parts, no, of the CE amplifier, we have other two-port parameters. The other two-port parameters shouldn't usually be affected by the CPI, but this one is going to be influenced by the input pole. Bakit? Kasi yung VBE mo nagbabago, di ba? And your GM, your overall transconductance, actually depends on how Vin, right? So the transconductance is the output current versus the Vin. And the Vin is over here. So, ibig sabihin, yung transconductance mo actually mababawasan kasi binawasan mo na si Vin dito sa simula pa lang. No? Tapos ito yung GM na nakakonect dun sa, ito yung actually nakakonect dun sa amplifier which is connected to GM. So, we don't expect it to still be just GM kasi nga mababawasan si Vin before we go in. So, it turns out, no, that if you do, well, that math, basically, no, we know what VBE is. It's Z pi over Z pi plus RS. And we can expand that to get what we had earlier. But we have this, no? What we had earlier is this, no? So this is Z pi over Z pi plus RS, no? So this is our new GM, no? So GM is at low frequencies reduced by R pi over R pi plus RS. We know that, no? We've seen that in the non-frequency response solutions to the small signal. But what's new is we add this output pole. We add this pole, no? And it's the same pole that appeared in the gain, which kind of makes sense, no? Because it's GM. It's GM, which makes up part of the gain, No, remember this equation? So, the input impedance, of course, also still changes. We know this. We just add, it's just RS plus Z pi, and then we expand this to solve for the form that gives us basically a Z0, and it turns out that it gives us a omega P1, no? It gives us a pole and a 0, no? So the input pole, the input impedance turns out to have a 0 at 1 over C pi RS parallel R pi, and the pole at 1 over R pi C pi. No? So that's interesting. And the output impedance is still the same as the output impedance for the from the addition of CL, no? So it's RC over 1 plus SRC CL, no? And if you, well, as I mentioned earlier, no, if you multiply GM and Z naught to try to derive the voltage gain, you will get the same as earlier. No? So we have GMRC, R pi over R pi plus RS. No? So this is the original gain. This is the low frequency gain, but affected by the R pi and the RS. No? Affected by the voltage divider here. And then we have this pole. And we have the other pole. No? From which we obtained from GM. No? So this pole will be C pi times RS parallel R pi. All right. So that's basically the response of the C amplifier. No, and we summarize that here. So again, no, GM was affected. It adds a single pole to GM. It adds another pole, a different pole, to the output impedance, which we've already seen from the CL only analysis earlier. And we also have the effects on AV, which is just compounded effects on GM and Z out. Interesting thing happens for the input impedance, in which we get in which the pole that was introduced to GM is actually a 0 for the input impedance, and it has 1 plus R pi and a C pi over here. All right. 1 plus S R pi C pi. No? So malito. All right. So lastly, actually no, not lastly yet. Let's talk about the Miller capacitance. So the Miller capacitance is a capacitor, is what you call a capacitor that you put in here. No? Between the base and the collector, you put in a capacitor. You call that the Miller capacitance. And, well, okay, it has an interesting effect. To derive it, it's actually pretty long, no? But, okay, you can start with deriving VBE, no? So you KCL at VBE and you KCL at V out, no? And you get two equations from that, no? Tapos, we solve for V out from VBE, no? So we isolate this right here, no? Because you have one equation, no? The this part, which doesn't actually which only has V out and VBEs, no? So you can isolate V out over VBE from that to get this looking well, again looking like this, no? And we already have things that we can interpret from this, no? Even without the RS resistance, no? So if we assume basically that the source is ideal, no? If we assume that the source is ideal, um if we assume that the source is ideal, what's gonna happen is that this will be the overall gain of the system. So alam na natin, no, we basically already have an idea kung ano yung ginawa nung Miller capacitance. The gain at low frequencies is still the gain that we've always expected from a CE amplifier. It's GMRC. It's over here. But we get a 0 and we also get a pole, no? Let me erase this so that we can see the 0 and the pole more clearly. The Miller capacitance adds a 0 that is GM over C mu, no? It's basically a very large pole, no? Bakit? Kasi GM is, okay, you'll see that later, no? I'll explain it later, but omega Z is typically very large because GM beats out any other capacitance, any other resistance, no? We typically know this, right? This is always less than any other R, no? Almost typically less than any other R. And we also have RC times C mu, RC times C mu plus CL, no? So this is the other effect of the Miller capacitance. It leaks out to CL, that's basically what happened, no? It adds to the capacitance of, it added to the capacitance of the output, no? This is, remember, no, we used to have a capacitor, a pole, no, nung CL pa lang, wala pang CMU, we had a pole like this, no? That pole turned into this. Basically, CMU leaked into the output capacitance, no? It got referred to the output as well, no, in addition to creating a zero, right? So now let's try to get VBE versus V in, no, but V out interferes here, so the algebra is a little complicated, no. That's also part of the reason why I decided to just use the slides here, because I couldn't get the video to be very short. Anyway, from the math, no, you'll get something like this, no. So kailangan mo pang i-expand ulit to kasi ipapasok mo si SCMU doon, but you'll get something like this. All right. And this one is already what you want, no? And okay, I'll show you. Ito, this is your low frequency gain. No, overall low frequency gain. It's GMRC R pi over R pi plus RS. It's your normal gain, but you have the voltage divider over here. Familiar with that? This is the zero from the Miller cap. No? We expect that to appear because we've seen that appear in the case ng wala pang RS. But we have this thing, no? The Miller cap actually modeled the poles at the bottom. Hindi na siya too particularly easy to separate poles, no? We're gonna have some we're gonna need factorization, no, to occur down here, no? So but we know to expect two poles from this. Bakit? Second order siya, no? So fundamental theorem of algebra, second order, dalawa yung magiging roots, right? And the roots of these is always it's going to be the frequency, no? The pole frequency of interest, no? So we try to interpret this, no? Or we try to shape this into a form that we're familiar with, no? Which, we've already done. This is a zero, and this one should be transformable into two pole contributions, no? Which is exactly this, no? So we have an A0, that's that one minus S over Z, tapos 1 over S over P1 o 1 over S over P2, no? So this is a factorization, no? What we do here instead, no, because this is a difficult factorization, gonna have to use the quadratic formula with with a lot of these, no. What we'll get really is this, no. What we expect the bottom to be is we're going to assign the poles to factors of these, no. So we expect that 1 over P1 P2 has to be equal to that, and 1 over P1 plus 1 over P2 has to be equal to that. By the way, this is just foil mo lang to, no? So multiply mo lang tong dalawa, expand, you get this, no? So the approximation that we make is 1 over P1 should be around like this value, and 1 over P2 should be around that value. Bakit? Kasi they're separated by a plus, no? But as far as I checked, no, doing this makes this incorrect, no? So this is an approximation, no? That's why we write this, no? That's why it's an approximation here. So basically, what do we get from that? A0 is still the low frequency gain that we expect from a CE amplifier with the source resistance. Omega P1 is 1 over RC C mu plus CL, no? If C mu is much less than CL, then it still becomes 1 over RC plus CL, no? But C mu could also still be interpreted as leaking into the output, no? This is more accurate. Now, it also adds a second pole, no? A second pole, that's like the one that we had for the input capacitance, no? Ano yung pole na meron tayo dun sa input capacitance? We called it omega P1 at the time, but if I remember correctly, the pole was C pi RS parallel R pi. The pole for the gain, by the way, no? This one of the poles for the gain, for the voltage gain. So we got this, no? Dun sa derivation natin nung may input capacitance tayo dito, no? Remember we had this, right? So now, basically what we can interpret as having happened is because we put in a capacitor C mu shunting the C mu connecting the input side and the output side, no, the base and the collector, it basically introduced a C pi, no? But not just any C pi. C mu turned into a C pi with an amplification. This is your gain. You amplified C mu and put it in the input is basically what happened, no? And you call that the Miller effect, no? So what happened? We put in C mu, and it turned out to be semi-equivalent, approximately equivalent, to putting a C mu here and a C mu times 1 plus GM RC here, no? So you multiplied it by a gain and put it here, no? And basically you can remove that. This is the Miller effect, no? So you put the C mu there and you put the C mu here times the gain of the BJT, and that's the Miller effect, no? It adds two halves, one at the output, one at the input. The input one is extremely large. All right. So, expected magnitude response from the presence of the Miller cap, we get a 0, no? The 0 that we've seen earlier, no? And then we have the first pole, no? The original output pole, and this one, the basically the referred input, no? So the Miller cap referred to the input, no? So you get this. So you amplify the Miller cap, put it at the input, and then just as the frequency response of the input of the amplifier with the input pole you had in the first place, you put it there. All right. So we get the influence of one pole and then two poles, and then it's offset by the 0, no? So babawasan ulit nung 0 yung slope. Now, bakit natin nilagay sa dulo yung 0? Well, depends on the exact values, but GM over C mu, we can assume C mu is a little smaller than the other capacitances, and GM, no? Remember, 1 over GM tends to be a much smaller resistance than the others, no? So if we switch it around like that, no, GM tends to be higher than the other 1 over Rs, no? So we can usually put the 0 at the latter end. Now the phase response is basically 3 downward 90-degree contributions. Bakit? It's downward 90 degrees for P1 because it's a 1 plus S, no? This is a downward 90 degrees again for P2. Bakit? Kasi it's a 1 plus S as well. Kaso, 1 minus, the form that we had earlier is 1 minus SC mu over GM, right? So, minus yung nasa gitna, which flips the phase response for the 0, leading us to have this, no? Instead of an upward climb, like that one, no? So, if it were a plus, right, you would expect na pataas siya doon, right? You would expect that we climb up instead, no? But that's for a plus na 0. Kaso, hindi. We have a 0 that's a minus, so we still go down, and we get another minus 90 degrees down here. All right. But it usually probably doesn't matter kasi at this point your gain is so far down that you probably don't want to be using that part of the amplifier anyway, right? All right. So, lastly, no, anong ginagawa ng mga coupling capacitor natin? Well, our coupling capacitors, eto, no? So, by the way, again, a coupling capacitor is a capacitor that you use in order to remove the DC contribution of the input port, no? So basically, we have a resistor divider biased C amplifier with emitter degeneration as well here. And to use a resistor divider as a bias, kailangan nating i-decouple yung input using an input capacitance. Now, anong ginagawa nito dun sa gain natin? Well, it adds a 1 over j omega C in doon, katabi nung Z in, no? So it becomes a resistor divider as well. Okay. So it becomes a resistor divider, no? So we have that now V in is equal to Z in over, actually bakit Z in yan? Let's call it RN. Assume na wala pang walang parasitics yung BJT, no? First, let's do that, no? So meron tayong R pi over R pi. Actually, original Rn over original Rn plus 1 over SC in. Right? So, what we get from this really is no? So SCR over Rn plus 1 over I. Okay. SCR plus 1. Yan. No? So, we have 0 at 0. We have a pole at 1 over RC. No? So, basically, the input coupling capacitor adds this, no? It adds a minimum frequency at which hindi pa maganda yung gain mo kasi malakas pa yung kinakain ni Cin, no? How do we prevent that? Well, we want Cin to be very, very large, no? So when we use an AC coupling capacitor, you usually would like Cin to be very, very large para mababa yung no? Para mababa yung pole, no? Para mababa yung pole so that you have a midband, no? So basically this is poles of the amp itself, and this is from the bypass cap, no? So you want this to be very, very far back, right? So you'd like the 1 over j omega Cin to be much less than Zin, which means you want Cin to be very large, or the frequency to be larger, no? So that's what happens there. You can see, no, typically, basically, you'd have this, no, as the magnitude response of the amplifier itself. Kung may coupling capacitor ka, then you would have as an S, like a 0 at 0. So pataas ka magsimula, tapos yung contribution ng pole is i-flatten niya, right? Kasi magdadagdag ng pag-ganon yung pole, no? So i-flatten niya yon, and you get some midband, no? You get a midband that actually has your ideal gain, no? So that's what the input capacitance does. All right. So if you add a bypass capacitor to the emitter degeneration, no? di ba ito yung gain nung yung basically mid-band gain, no? I'm not going to call it low frequency gain anymore because it could be the mid-band from the existence of Cn. So this is the mid-band gain, the gain of interest, the gain of the gain that you actually want. And it would be ito will then be replaced with a impedance ZE, no? Which changes our gain, no? But typically we wouldn't want this, just like we didn't want the Cn to lower our gain at some of the low frequencies. So what do we do here? Well, ang mangyayari dito, we'd like 1 over j omega CE parallel RE to be close to 0, which means that CE also must be large, no? CE also must be large, no? But basically, ang gagawin lang naman netong CE na to is since the gain, the input resistance, and the output resistance, and the transconductance are all affected by this factor, no? In the um in the in the typical emitter degenerated C amplifier, then babaguhin nung emitter degeneration impedance mo ngayon such that maglalagay siya ng pole at 0. Actually, let's just solve it. No? So 1 plus GM. This becomes RE parallel CE. No? 1 over SCE. So then this becomes RE over SCE over this is RE plus 1 over SCE. This becomes SC RECE plus 1 tapos RE lang dito, no? All right. So for the gain, no, it should add a nasa baba to. So RE this becomes okay, it adds a pole and a 0, no? If you do that later on. All right? But anyway, guideline is typically bypass capacitors and the input capacitor, you'd like it to be very, very large. All right? So that ends this lecture for now, and I will upload the next video for the last lecture soon as well.